We're going to start talking about the alcohol functional group and what they are going to do and how they're going to behave a little different than some of the other functional groups. Now, the alcohol functional group is going to have attachment to a carbon chain, for example, that I'll indicate as R. And they'll also have a partial negative charge on the oxygen because the oxygen is more electronegative than the hydrogen, so there'll be a partial positive charge. This is a very strong interaction because this oxygen here is very electronegative, and it's going to pull the electrons away from this bond here, and that means that this is going to be a bare hydrogen, a bare proton essentially, because the electrons are going to be pulled over here. So this is a very strong positive charge. What that means is that this positive charge is going to be able to interact. This positive charge is going to be able to interact with other compounds that are negatively charged, and that's what we can interact. That intermolecular force is going to be hydrogen bonding. And this is one of the strongest intermolecular forces that exist is hydrogen bonding. So we have to keep that in mind when we're looking at these different compounds. So some of the properties of alcohols, again, they're more polar than hydrocarbons because of that hydrogen bond attached to the oxygen. Melting points and boiling points because of that very strong intermolecular force that is now possible. And they're also going to be more like they're going to change the solubility in water because that alcohol group, at least with small organic compounds, they're going to be able to interact with water because of that hydrogen bonding capacity now of that molecule. The functional group of alcohol, it is a oxygen and a hydrogen that is attached to a carbon. So we can have different types of alcohols. We can have a primary alcohol, which is at the end of a chain. We can have a secondary alcohol, which may be coming off of something that is in the middle of a chain. And we can have a tertiary carbon or a tertiary alcohol where we have something hydroxide coming off of a carbon that's attached to 3 other things. So there's the primary, secondary, and tertiary alcohols. Electronegative elements are results in that polarity, those polar bonds. And again, if we're looking at the fluorine here is going to be kind of the center stage here. And if we draw lines through the elements down the periodic table, and again, I like to have hydrogen here as kind of over the boron. These lines traveling from fluorine to this other line, traveling from this line to this line, from here to here, from here to here, from here to here. Whenever we cross a line, then that means that the compound in one line to the next is more electronegative than the other. And then that means that there'll be partial charges in bonds that are associated with those different elements. Those electronegativity changes are going to then influence the function and the characteristics. So basically, the more electronegative, the more of that electrons are in that area. So you can see with ethyl alcohol here, this region, that oxygen is going to have a higher density of electrons. You can see that with a red color there. Whereas this blue spot is going to be kind of colder, lower electron density. That means that there is more positive charge in that. So that's the partial positive, partial negative of that ethyl alcohol. So, ethyl alcohol or ethanol is soluble in water. It's because of these charges that allow it to be soluble in water. Phenol is not necessarily soluble in water because it's got this large group of organic hydrocarbons that are not electronegative or positive, right? But we have this group that is, but it's still not enough to kind of make up for and allow water molecules to kind of surround that compound. Diethyl ether, we have this negative, partial negative charge here with that oxygen is able to pull some of those electrons from the carbons, but the charge on the top, the partial charge on the top, is pretty minimal. You can kind of see the difference in colors here, and that's because it's able to spread that positive charge out between more regions. So generally ethers are a little less, they're less polar, they don't have a polarity to them really. And so you can see chloromethane has large polarity here as well. So again, hydrogen bonding, that discussion that we just had with those molecules we just talked about, hydrogen bonding has an influence on boiling point. So propane here, just only hydrocarbons, it cannot hydrogen bond because in order to hydrogen bond, you have to have a hydrogen attached to either an oxygen, fluorine, or a nitrogen. So hydrogens like to have FON, F-O-N, right? And in order to do that, so in this instance, we don't have hydrogen bonding because there's no hydrogen attached there. So there's a little less of an influence on the boiling point when we go from propane to dimethyl ether, even though the molecular weight is similar. And then when we go up here to ethyl alcohol, now we can have hydrogen bonding because it's attached to an oxygen. The molecular weight is very similar, but the boiling point is increased substantially. And then again, when we go to water, boiling point's increased because essentially we have two different atoms in that molecule that can hydrogen bond. It's very polar, and it's a strong interactions that can be made in water because of that. So again, when looking at something that if we want to decide if it's going to be water soluble or not, we generally want to be able to look at the compound and see how many hydrocarbons there are compared to how many polar groups there are that are going to be able to hydrogen bond or be involved in hydrogen bonding. So methanol is a very short compound. You can see it just has one carbon, but it has this polar alcohol group on one side, and so it's very soluble in water. Whereas heptanol, it's got this much longer carbon chain here, and then it has this polar group on the end. So it's not going to be water soluble because you could imagine water is really only going to be able to interact with it on this side of the compound, but not on the rest of the compound. So it generally will not be water soluble. If you can add additional alcohols, for example, if we're looking at butanol, there's limited water solubility here, but if we add two alcohol groups onto both ends of that, that gives some solubility, increases the solubility into water. Because again, same kind of thing here. If we were to add, an OH group here, and maybe one in the middle, that might help allow at least for some of the water molecules to interact on the top, potentially. Maybe we need to add another here on the bottom, but that would increase the more hydroxide compounds that we add, the more water soluble that long chain is going to be. So I want you to think about this question here. Maybe pause this and read the question, think about it, and then so unpause, and here's the answer. So how would we figure this out? What do we need to do? What kind of reaction is this, and how do you write it out? Well, first, what is ethylene? Ethyl, that's two carbons, so let's start there. And it's ENE ending, so we're going to have a double bond. So we have this compound right here. Ethanol, we're going to do that. So to name that, we have carbon, methyl, ethyl, and then an OH group. So that makes it ethanol. Okay, so we have ethanol, right? This is going to be the final product. How do we turn this into this? So what kind of reaction can we have? So we looked at double bonds before, attaching, interacting, and we can hydrate that double bond. So ultimately, we want to add water to that double bond. And so one of the hydrogens is going to attach to the carbon, and the other oxygen is going to attach to the other carbon. So here we want to break apart this bond and attach that to there, and these electrons will, from the double bond, will flow down to the hydrogen, and we will make this final alcohol product. So this is going to be, we have two compounds, 1, 2, we end up with 1. So this is going to be an addition type of reaction. Usually in organic chemistry, this is going to happen with an acid catalyst, and that just helps to break apart that water molecule a little bit and lower the activation energy for that. So if we look at, we can also look at alcohols. When we start with an alcohol, we can kind of do the same thing in reverse, right? With an acid catalyst, we can help to break apart and form water, and that helps to break apart that carbon hydroxide bond, and to then form an alkene, where we strip off those molecules and form water. So this would be a dehydration or also an elimination reaction. That will also allow us to do, the reverse reaction as well. Okay, so looking at this, what will be the major product of a dehydration reaction here? What is your guess? So take a second here to pause this and think about how this will work. So the major product here is going to be where the major product will result in higher order carbons having double bonds. What do I mean by higher order? That means that they're attached to more other high molecular weight things. So if I'm looking at these three possibilities, so I know that this hydroxide is going to come off, right? And then this carbon is going to have a double bond attached to it. So it's either going to go to this carbon, or that carbon for a hydrogen to pull off to form that water. And so where will a double bond be attached then to a carbon with more carbon interactions? So 1 and 2 are really the same, right? They're methyl groups. They're not attached to anything else. So if I made a double bond between this initial carbon that's attached to the hydroxide and the other 1 and 2 carbons, it's going to be the same product, but they're not attached to anything else. Whereas if I make a double bond between the initial carbon and carbon 3, then that carbon's also attached to another carbon, and then that means that carbon 3 is a higher order carbon. So these reactions generally run with an acid catalyst, and then we're going to, this is the double bonded carbon. So this could end up forming in either the cis or trans form, but I've just drawn it out here. But ultimately it doesn't matter, because if you draw it one way or another, the final product is still going to be the same. Again, I mentioned earlier that there is a carbon order and how you can name these different compounds and define and determine what is a higher order carbon. You were asking me, here we go from the primary carbon, where that carbon in that first instance on the far left, it's just attached to hydrogens. So this is referred to as a primary carbon. Second carbon is attached to 2 other groups. It's referred to as a second carbon. This third carbon is attached to 3 other groups, so it's a tertiary carbon. And then finally there's quaternary carbons, where they're attached to 4 other groups. So this group on the far right is the highest order, the highest priority carbon. Just to mention, in the future, also nitrogen also uses the same naming system. We could write the same thing with nitrogen. And generally we have that lone pair, so that would be a primary, secondary, tertiary. And you can also have a quaternary nitrogen, but that means that it had to have given up those lone pair, one of the lone pair of electrons, and so then it's going to be positively charged because we have 1, 2 lone pair that usually keeps as its own, but it's gonna, if it's gonna share one of these, it's gonna share this one, then it's going to lose that electron and it's going to gain this positive charge. So quaternary nitrogens are always positively charged. So when we're looking at primary, secondary, tertiary alcohols, it's going to be based on the number of carbon substituents bonded to that hydroxide bearing carbon. So for example, primary alcohol is on a primary carbon, secondary alcohols on a secondary carbon, and then the tertiary alcohol is on a tertiary carbon. So we can't have a quaternary alcohol because the carbon would be attached to too many things. So on this, maybe pause, take a few seconds, identify the primary, secondary, and tertiary alcohols on this page. And I'm not actually going to give you the answer. If you need the answer, then you can come to my office hours. But just making sure you're not just watching the video without actually doing these learning checks. What we're going to look at now is looking at the acidity of alcohols and phenols. So they dissociate slightly in water, and they establish an equilibrium between neutral and these anionic forms with a negative charge. They're not very acidic generally; they're weakly acidic, but they do have some properties of an acid. So oxidation reactions are very important organic and biochemical reactions. They're often seen in the metabolism of different organic compounds or biological compounds, and in this process in biochemistry, it's an important area where we can harness energy from this process. Where we breathe in oxygen, for example, and we breathe out carbon dioxide, that process is where we can harness some energy. Oxidized molecules are generally more stable than non-oxidized molecules, and in that stabilizing that molecule, that energy difference is what's harnessed. So when we're looking at oxidation, really a good way to think about this is just that carbon has basically acquired more carbon to oxygen bonds. So you can see in alcohol here on the left, we have 1 carbon-oxygen bond, and on the right, we have 2 carbon-oxygen bonds. So that oxidation state of that carbon has increased from the alcohol to the carbonyl compound. So think about this. Why do you think, what happens to electrons when they're associated with oxygen versus when they're associated with hydrogen? So why would an oxidation release energy? Think about that. And the answer is that electrons pull in closer to the positive charge of the nucleus. So the closer the positive and negative charge of that compound, of that atom and the electrons, the more stable that those two components, the protons and the electrons, are. And so that stability is what actually is involved in releasing that energy. So we go from kind of a higher energy state to a lower energy state in that type of system. So we really generally don't have tertiary alcohols reacting as oxidizing agents because they don't have a hydrogen on an adjacent carbon in which it can bond to. And we know that carbon's not necessarily going to form 5 bonds. So generally, tertiary alcohols don't oxidize very effectively. Where second alcohols still do, because we have that adjacent hydrogen in which we can pull off, form water, and then we can also still form a double bond with that carbon, because then it still only has 4 different bonds. And primary alcohols, obviously there are multiple places where that hydrogen can be pulled off of to form that double bond as well. You can get an initial primary alcohols can be converted into aldehydes if there's carefully controlled conditions, or carboxylic acid if excess oxidant is used. Alcohol has one carbon-oxygen bond in the primary alcohol, slightly oxidized to an aldehyde, right, where this is kind of a carbon on the end. It has two carbon-oxygen bonds, and then we get on this carboxylic acid, we have 1, 2, but then we've added a third here. So that is the most oxidized that we can get, outside of then turning this into carbon dioxide. And that's, folks, what we breathe out. And that's why we breathe out carbon dioxide, because we're able to harness all of the energy out of that carbon molecule that we can. Okay, so what's the product going to be of the following oxidation of the following compound? What functional groups are formed? What's going to happen to this? Draw it out. Think about this before you unpause this section. Okay, so another kind of problem you can do to work on these types of questions, draw out the complete oxidation of ethanol that occurs in the bodies of people above 21 who have consumed alcohol. So what is the complete oxidation of that going to look like? So when we consume ethanol, what we do is that we have an oxidation occur in our bodies. We take this carbon to hydroxide bond, that primary alcohol is then oxidized to an aldehyde. So we go from 1 bond to 2 bonds with oxygen. So this is more oxidized. Acetaldehyde is actually a compound in our bodies that make us kind of feel hungover. This is what we're gonna get if our body is not able to process this and eliminate this from our bodies effectively. This process is generally regulated by an enzyme called acetaldehyde dehydrogenase. Our next process is we have an additional oxidation. You can see that carbon has 1, 2, 3. So we go from 2 carbon-oxygen bonds to 3 carbon-oxygen bonds. And this is the additional oxidation into acetic acid. Acetic acid is actually more easily eliminated from our bodies, and we can kind of, this doesn't usually stick around in our blood as long. What I'd like you to do in here is look at these different organic compounds, and based on, order these in order of how you base them on the lowest melting point to the highest. And I'd just like you to kind of take some time to write this out. Again, I'm not going to go over the answer in this lecture because you should be able to figure that out on your own. Come to my office hours if you cannot organize these, but based off of what I've spoken to you about so far, you should be able to figure that out.